Hello everyone, I'm Mojtaba and welcome to another episode of A Sip of Chemistry. I'm really grateful that so many great scientists have taken the time to share their stories, insights, and thoughts with us. Today, my guest is Dr. Cynthia Jameson, an emeritus professor of chemistry from the University of Illinois Urbana-Champaign. She's been working on nuclear magnetic resonance (NMR) spectroscopy since 1963. Out of all the incredible research she has done over the past few decades, one of her biggest contributions to science is mapping the NMR chemical shifts across the entire periodic table. If I were to list all of her achievements, awards, and honors, we'd be here for an hour. But just to mention a few, she received the Eastman Award for the most outstanding chemistry graduate student, was recognized as Woman of the Year by the University of Illinois, and in 2000 she became the first woman to deliver the Vaughan Lecture in the NMR section of the Rocky Mountain Conference on Analytical Chemistry. Beyond her research, she's also been a strong advocate for women in chemistry. She designed the postdoc institute at the University of Illinois at Chicago to support female postdocs and help them transition into academic positions. So I invite you to join me for this exciting interview as we dive into her journey in science and other fascinating aspects of her career. Hello, Professor. Thank you so much for agreeing doing this interview. And please tell us more about yourself. Where did you go to school? And tell more about your educational background, please.
Okay. I grew up in the Philippines, and all the time when I was young, I was very much into math and sciences. So my favorite subjects were math and physics in high school. Anyway, when I finished, I went to the university and took the entrance exams for the University of the Philippines, which is a state university, in order to try out for, well, not just for entrance, but also for scholarships, because we were very poor and my parents couldn't afford to send me to university. Anyway, they had a new program, which was a 5-year program that involved chemistry and engineering. So together with the regular Bachelor of Science in Chemistry, they had the courses in electrical, mechanical, chemical, engineering. So I thought that was interesting. So I decided to go into chemistry. I had not taken any chemistry before that time. And then when I finished, of course, I've always dreamed to be a teacher, teacher, either a math teacher or a science teacher. And so my thoughts were that I would just stay at University of the Philippines, become a lecturer, and give courses, the usual lectures and so on, laboratories. But two brand new PhDs from the US came back and were professors at the university. And I was so impressed with them. I said, I want to know what they know. And so to make a long story short, I got to know at least one of them very well. The other one I took courses from, and learned a lot about various things. Quantum mechanics, and he was the guy. He was a physical organic chemist, name of Octavius Pascual, and he told me at that time, it's 1950s. Okay, he said there's a brand new spectroscopy that's coming, and it will change the way we do chemistry, and that was nuclear magnetic resonance. And so because I wanted to know what they knew, I had to go to the US for a PhD. So of course, we couldn't afford to for me to come to the US. So I applied for a Fulbright scholarship, and I got it. And so I decided to do my PhD somewhere in the US. And the interesting thing is that many of the well-known universities didn't have any women at all at that time. So there happened to be a big exhibit in the hall in my university, and it said the Big Ten universities in the United States. And so I looked at each one of the exhibits showing the campus and telling about each campus, and I said, "Oh, those must be the best universities in the United States." I didn't know it was related to football. So I ended up applying in all of the Midwestern universities and received teaching offers, teaching assistantship offers from them. But I decided to go to Urbana-Champaign because there was this guy who was the head of the physical chemistry division. His name was Herb Gutowski. He was at that time pioneer in applying nuclear magnetic resonance to chemical problems. And so since I already had this bug in my head that NMR will change the way we do chemistry, I decided that I will go there and I will work with him. And that's how I ended up with a PhD in physical chemistry with Herb Gutowski. And then from Urbana, when I finished, well, first of all, I didn't finish right away. Because I was there for 4 years, but I met my husband, while he was a graduate student and I was a graduate student. He was my TA and grader in one of my courses. And so I got married in June 1963 before I had written my thesis. And then I left, but I already had a postdoctoral appointment with Martin Karplus in Columbia University. So I went with my husband to New Jersey, where he was working for ESO Research Laboratories. And then, of course, I had to go back to the Philippines because on a Fulbright, you can only come on an exchange J visa, it's called exchange visa. And the requirement is that you spend 2 years in your home country before you are even allowed to re-enter the United States.
Mm.
And so my husband and I went back, and I was teaching at the university where I graduated, and he was teaching in a Jesuit university, which had very excellent facilities and students, and we really enjoyed that time. He wanted to be a research laboratory in industry. That's what was his original goal. But he enjoyed teaching so much, and so did I, that we decided we'll go back to the United States and we will be tenure track faculty members and do not only teaching but also research. So that's how I ended up in academia.
Yeah, that was a nice story. So gas phase NMR is one of your area of expertise. Xenon 129 isotope, that's one of them. So why did you find the gas phase NMR important to do the research?
Well, you see, my whole take on doing research is to try to do things where it's actually possible to do alongside with experiments, theoretical calculations to truly understand what you're observing. Okay, so that means using systems which are simple and where it's possible to do calculations to see what information you're actually getting from the experiments. And so it turns out that nuclear magnetic resonance chemical shifts tell you a lot about intermolecular interactions. So it's used for various things nowadays, of course, because you can, and the chemical shifts tell you that this environment is different. And how different, of course, depends on how you interpret the results. So in order to have something that is not only measurable in a rigorous way, not too complex a system, but also being able to do calculations. So the only system where it's possible to do that is when you are in the limit of binary interactions, only two at a time. And what more simple system can you think of than an atom? Okay, so xenon, because it has so many electrons, has a very polarizable uh, electron clouds, and therefore it gives very large chemical shifts whenever it encounters anything. So, I imagined that it would be extremely useful for finding out about environments. You put it in solution, you find something out about the liquid structure. You put it put it next to a protein, and you find out what kind of pocket it's embedded in. But you can't do any calculations on those things. They're too complicated. So we went into the gas phase. In the limit where only binary collisions give rise to whatever you're observing, and then you can do calculations in closed form. So that's why xenon.
I see. Yeah. So, and somehow the question that I'm asking is a follow-up of what I asked about the chemical shielding, nuclear shielding. This is also a big portion of your research. So,
Yes, I started on nuclear magnetic shielding. That's what it's called. It's the response of the at the nucleus that's observed by the nucleus, response due to the electrons around it. And it's a combination of simply total density of electrons, which is a diamagnetic part, but there's also something which has to do with the what is called the paramagnetic part, which is more important when you go into molecules and interactions. And when I was a graduate student, this is what I did for my thesis, because at that time, the very first xenon compounds were being synthesized, very first. And my advisor knew about, from one of his former students, knew his experiments before they were even published in Science. And the chemical shifts were so large for xenon in these compounds, xenon fluorides, oxyfluorides, and so on. And so he said, we need to find out, is there something goofy about the bonds in this noble gas compounds? They've never been made before. So maybe there's something unusual about them. So we will want to use the chemical shifts to find out something about the bonding. Okay. And so I told him, well, I cannot do the calculations and then interpret what we are seeing unless I can do it for the entire periodic table, because that's the way I think. Never do single point anything. Always do things in series, so that what you observe is something that you can understand in a way that is systematic. So we have to do the whole periodic table. And so I started looking into the what is observed at that time. How large is the chemical shift range for every particular nucleus? Of course, at that time, it was only a few nuclei had been observed. Protons, of course, hydrogen. There's some carbon. There was some cobalt even at that time, because it was easy to see the signal. But very few elements in the periodic table had become NMR nuclei. Okay, so I had to deal with a very limited amount of information, and I decided that, given what I can see, maybe there is a periodic behavior in the chemical shift range.
did you see anything? Did you see any systematic trend?
Not until I did the work. Okay. So by chance, I was in Columbia University and just browsing through the library, and I happened upon a page in which they were looking at the spin rotation constants, which turns out to depend on 1 over r cubed, where r is the distance of the electron from the nucleus. right? And it turns out that chemical shift, part of the chemical shift has the 1/r³ operator in it. And so once I saw that information of how to get 1/r³ for the atom, uh, um, from these observables that you can get from atomic spectra. So I just looked into the table table of atomic level energy levels and pulled out these numbers, and when plotted across the periodic table, they went in a zigzag fashion going up as you go to the right of the periodic table and down in the periodic table, like ionization potentials. And so my xenon fit right in. In other words, there's nothing special about the bonding there. It's just the way it happens because it's in that part of the periodic table. And the chemical shifts are huge, in the thousands, whereas for protons it's only 1 or 2 or hundreds of ppm. Yeah.
Okay, interesting. So you did a lot of work on, actually to understand all these things.
I've been in xenon for a long time. From the time when I was a graduate student, I finished in 1963. Yeah, until I was a regular faculty member, I was doing a lot of work off and on. We go into xenon.
In your opinion, what's your most significant contribution to the science, to the NMR research that
I
you've
think
done?
it's the understanding of chemical shifts. Yes. Um, not only the isotropic part, which is where the signal appears in the radio frequency spectrum, but also the anisotropic part, which gives rise to different line shapes. So yeah, I think that's my most important contribution, because I have looked at NMR chemical shifts in the gas phase, and for xenon in various in things like zeolites, nano cages, nano channels. So you study adsorption and diffusion of atoms and molecules through channels of of various solids, crystalline materials, or not necessarily crystalline, could be polymers, whatever. You put xenon in it, you find out what's going on. And that's because I understand how it responds to the environment.
Is there any work that you have done and you got excited about it, about the results you're finding, but you felt that the community, in the community, didn't get the proper attention? Is there any kind of project, that research that you did and you encountered such experience?
Yes. Well, probably our work in, let's say, spin relaxation times. Again, we did this in the gas phase, because it's actually possible to do calculations of the collisions that occur in the gas phase, and find out and calculate exactly what is the resulting spin relaxation time associated with that density and that temperature. So again, going into as fundamental a system as possible, we were looking at the spin relaxation times in the gas phase for things like methane, carbon dioxide, carbon monoxide, nitrogen, things like that. But we also looked at xenon in the presence of mixtures, including oxygen. And it turns out that's a very important paper, the xenon in oxygen. And nowadays, people always refer to it because they are using xenon for imaging lungs, And so relaxation time has a lot to do with how well you are able to do imaging, magnetic resonance imaging. So magnetic resonance imaging of the respiratory system makes use of our spin relaxation times of xenon in oxygen. So sometimes, you do something and it doesn't, the consequences don't show up until 20 years later.
Yeah, that's interesting. Yeah, but eventually, actually, it got the attention, and researchers in the community found it interesting, useful, and they are using it. Yeah, yeah. Now, I would like to ask a few more questions related to other activities you've done and also the science generally. So, women in science, it's been always one of your concerns, and you've been active in this area to promote the presence of women in science. So,
It's because of the time when I entered the profession, very few women. In fact, when I was looking for a faculty position, there were hardly any women members of the faculty in chemistry departments in the entire United States. In physical chemistry, maybe there are as many as five, okay, the whole US. So it was just not thought of as a standard thing for women to be professors in science, at least. Maybe in the other fields they entered earlier, but and so I thought, this is such a shame, right? Because I felt women are just as motivated and just as could be just as brilliant as the guys, and they are not getting the opportunities. The world is not making use of them
yeah,
properly, and so I thought I would like to help. Because of my own experience, I would like to help women get into the professorate. Okay.
yeah,
And so at the time, we had a NSF advanced grant, which was to help universities change themselves institutionally in order to make it more inviting and warmer place for women in science and engineering to be professors. And so I was very active in that. And part of what I did was to prepare. Actually, I prepared something like 18 different workshops for postdocs, people who have their PhDs and are interested in going into academics. And so I prepared these workshops. They included everything: how to prepare your application package for a faculty position, how to start up a new lab when you first get some pointers on how to manage your teaching, um, uh, how to make good use of your time, because faculty member is required to do so many things that unless you are able to do time management, you are in trouble.
exactly.
How to write a good proposal. Uh, and also, so in these workshops, I invited individuals could be in private sector, could be in small colleges, could be in the university where I was, to form a panel and answer questions from the postdocs as to what it's like for them to be in that. What's your typical day activity, and how did you get there, and and so on. We even had for the postdocs the opportunity to present the kind of presentations they would make if they're invited to campus interview in front of a panel of faculty members who are acting as if they were members of the search committee and treating them with as if they were really candidates. And I think that was very helpful.
Amazing. Do you have any example of your attendees in your workshop that after all these efforts that you put in it, they approached you and said,
Well, yes, we had five special postdocs that we funded for 2 years, and there were other postdocs that attended the workshops, and several of them are now tenured faculty members
okay, amazing, that's great.
at places like Ohio State University,
Mhm.
Clemson University,
Yeah.
um, University of Tennessee,
Mission completed, right?
and also Puerto Rico.
Okay, amazing, amazing. When I was searching about your CV and your activity, I found something like an article-ish, something like that, with this topic: how to improve your student evaluations of teaching. What is it about?
Well, universities have at some point they started doing what is known as student student evaluations of teaching, so SET. So these are questionnaires which they pass around to the students at the end of the semester, and it's collected, and the data is used for promotion and tenure, for races, for all kinds of things. Okay, now it turns out what I did was to do a lot of research about SETs to see what is known about them. In other words, how accurate are the evaluations in terms of measuring how good a job the professor is doing teaching. And there's some very interesting research results, which lead to the following: that it's not just the cognitive part that is really important. In other words, that you are telling them in a good way about the subject, and making it so that it is understandable at their level, and so that you are doing things accurately without oversimplifying and things like that. That's the cognitive part. But there is a very important affective part, has having to do with emotions. In other words, if the students like your personality, like you in any way, they will give you good evaluations no matter what. Okay. And this is what the research tells us. So I'm trying to give advice to faculty members to work on the affective part, because obviously they're masters, they're experts in their field. They know what they're talking about. They can present a good lecture, but they have to always be thinking in terms of how do the students feel about them. So certain techniques as to make yourself more approachable, okay, to be more friendly in terms of dealing with students' questions in class, and basically it's important for them to like you.
Yeah, so it's not just the knowledge that the faculty member
Exactly.
needs.
Yes. It's
Yeah.
not it's not mainly the cognitive part, but the affective part determines whether or not you will get good evaluations. And in a sense, the two are connected, right? Because if the student feels good about the lecturer and feels good about the class, then he will be more motivated to do work in the subject. So one should not neglect the affective part.
Do you think the number of the publications matter, or the quality of the publication? In your opinion, um, which one comes first?
Well, I always say that quality is the most important thing. I mean, there's no point in publishing a lot of stuff that's junk. Uh, however, it's easier to count than it is to determine the quality. Very often, people that make the judgment simply count number of publications. However, there are things like citation index, which tells you something about how often that particular paper is used by others in their work, and that it is used as a surrogate for quality. It's not always a good measure, but it is some measure of quality. So it's a combination of how of uh, the journals in which you publish your work, high journals that have high profiles, uh, and also the how well you're able to reach and communicate with your community. See, every researcher has a community, people that read your work, that are involved in the same kinds of things, that make use of your work for their own. And so if you are able to reach your community very well, then you will have a lot of citations. Uh, so part of it has to do with, you know, being out there. You go to conferences, you give talks, you meet people, and if they have met you, they're more likely to read your paper. So there's a lot of things that go into it, and there's not one measure that is foolproof, that will always be, you know,
Exactly.
accurate.
Yeah.
But so you have to think about all of those things.
Yeah.
But for
Also,
me,
yeah.
unless I can be proud of the work, I there's no point in publishing it.
So also I learned that you've been part of many grant committees and boards. So uh,
Yeah,
But
I was a program officer at NSF, National Science Foundation of the US, for
mhm.
1 year. But I was also grants officer for 3 years in the Canadian system, the NSERC system.
Yeah, I'm familiar with it.
And I participated in their banting panels for postdoctorals. Um, I don't know how I ended up on the Canadian radar, but I was always willing to come, go to Ottawa in February. It's not a very nice thing to do, but that's how I ended up with it. Anyway, yes, it's interesting thing to be doing because you become acquainted with the ideas, the new ideas as they are coming out. Yes.
so as a grant reviewer, do you have your, is there any rubric for it, or you have your own actually rubric and you decide based on uh, what you think it should be?
There are universal criteria, of course.
Mhm.
The proposal has to be addressing a significant problem.
Mhm.
If it's not significant and nobody cares about it, so why should you fund that work? Also, what are the objectives? If sometimes the granting agency, especially lately, are concerned with uh, objectives that are headed towards applications towards national needs or something like that. But in the old days, at the time when I was doing it, it was primarily just basic fundamental science. Okay, something that does it contribute to the other parts of science? Well,
So it has changed somehow. Nowadays, you mean it's more application wise, something like that?
yes, nowadays applications are so important. Like there's such an emphasis on things like sustainable energy, like batteries,
Yeah.
drug delivery, things like that. We didn't think about those things in the early days.
Yeah.
Just do basic science
Yeah.
and move the frontiers.
This is why it's Faculty of Science, right?
But
That, that,
but the way to judge the proposals is the same, right? Because you are trying to find out whether or not the problem that's being addressed is a significant one, whether the methods that they are being proposed are appropriate for that question, um, and also whether the investigator has the right expertise to carry out the work, whether the investigator is in an environment where the work can actually be done. Um,
So overall, so you mentioned the change that has done over the time. You mentioned that how it has changed based on the uh, application or the answering a fundamental question. So overall, how in terms of uh, giving the money from the foundations, from the NSEC, for example, how has it changed? Is it easier now, or it's harder than uh, before?
it's harder because universities are actually expecting you to get more, okay,
mm,
than they used to, and of course, although the total number of investigators probably has not gone up by several factors, because after universities are, departments are no longer increasing in size. The most important changes are that the in the old days, uh, the the proposals were for single investigators, a single PI doing his own work in his own laboratory with his own team
yeah.
of students. But nowadays, there are very few of those that are funded. Primarily, what the emphasis is on multi-PI collaborative work across several disciplines, and either multi-PI with different departments in the same university, or even many universities coming together trying to solve a big problem.
When you receive a grant, when you receive a proposal, what's the most important part of that proposal for you? What's the game changer of that proposal? If you see the significance, or I don't know, the method, what?
If it's going to be a paradigm shifting work, in other words, we are thinking that this in this particular area, this is the right way of interpreting things.
Mm-hmm.
And by doing this particular proposed work, if it succeeds, it will change the whole way of thinking about that subject. That would be a game changer.
Yeah.
Okay, so I would, there's too much emphasis on novelty, it got to the point where the granting agencies and editors tell the authors, stop using the word novel to make it sound like it's really brand new and groundbreaking. But what we do is usually something that is standing on the shoulders of others that went before us. So in that way, it's not really novel, but you are adding something to it. So in that way, it is something new.
Yeah. So for the last question in this part, if you were a policy maker for giving the grants and awards to the researchers, is there any specific thing that you would like to change it or add to the policy?
I'm not sure that I have wisdom enough to suggest one thing that will make everything better. In the US especially, there is a lot of it's very hierarchical, the granting system. There are those, the haves have a lot, and the have-nots have almost nothing. And you have and this has to do with the stature of the institution where they're in. No matter that they are extremely good and doing extremely good work, they're not as recognized. The PI is not as recognized if they are come from a third tier or second tier institution. It's just natural, right? But the discrepancy is so huge. It's such a large difference, like the factors of even an order of magnitude. Okay, I like the Canadian system, which is much more equitable, so that you don't have grantees that receive huge amounts of money and those that receive hardly anything to be able to do their work. Everybody gets something to be able to contribute. I especially like the way you do your Canada Research Chairs, where even third-tier institutions can have a Canada Research Chair because they have one person that is particularly expert in one specific field. I like that. That would never happen in the US. We just don't. Those who have get more. So how to change that? I don't know. They've talked about it, maybe limiting the NIH grants to less than so many, no more than 5 RO1s, something like that. But one of the things that I would like to see change, but it's probably impossible, is the indirect costs. In the US, we have the university receive some fraction, like more than 50% of the amount of the proposal for what they consider their contribution to doing the proposal, like heat, light, and power, things like that. So at the beginning, in the old days, this was very small quantity, a small percentage.
Mhm.
And it just kept getting bigger and bigger to the point where universities became so dependent on it that they want their faculty members to just keep on getting more and more grants just for the indirect costs. And I think that's bad. I don't know if the Canadian system has actually adopted it. I hope they never do, because you know, it is just um,
I see.
you get a proposal funded for a certain amount, and you only get to spend a fraction of the amount to stipend for students and buying materials and so on. So those are two things that I would like to see different. You know, the indirect costs and also the huge discrepancy between the very well funded and the least well funded.
Yeah.
But I'm not sure how to do that.
I see. Yeah, that's an open question then. You are the first woman who delivered the Vaughan Lecture in the Rocky Mountain Conference, right? Is that true?
As a woman, I have done a lot of firsts. From the first time I started out until now, I'm still doing firsts. It's ridiculous, right?
Mhm.
It's modern times. I shouldn't be doing firsts anymore. But that's the way it is. It has taken, especially in the U.S., a long time for women to be recognized as being a natural part of science and engineering. And so that's why I'm still doing first. First to give an international conference on NMR after dinner talk.
Mhm.
Two of them. Anyway, I was the first woman to get the Emmett Gunning Awards at the University of Alberta, and and the interesting thing is that I was asked to be on a jury to award the Willard Gibbs Award
Mhm.
for the American Chemical Society Chicago section. It's a very, very old award. 1911, it was given to Arrhenius. Okay.
Yeah.
And so I looked at that. That was in 2006. I was asked to be on a jury, something like that, 2005, 2006. And I looked at the list of something like nearly 100 awardees. There was only one woman. Guess who? Marie Curie. After she had gotten her 2 Nobel Prizes, everyone else was male.
Yeah.
So I looked at it and I said, this is ridiculous. How come nobody even thought of any of the very good female professors and researchers to get the Willard Gibbs Award up to 2006? Only Marie Curie. I mean, she's an icon, and none of us think that we are ever going to be her equal. So, what about the rest of us? Just ordinary. Um,
That's true. Yeah, that's that's the sad part in the science that
but
Why we are
so
ignoring
I said,
half
I'm
of
going
this
to I'm going to do
population?
something about this because I'm on this jury. Um, and so I decided that well, we need to find the next Willard Gibbs, and I would like very much for that to be a female person. And so I looked at the national. I figured I would never convince my other jurors. There are 12 of us, um, to vote for my candidate if if they if the person did not look stellar to start with. So I decided that it would require a National Academy of Science membership. So I just looked in the National Academy of Science chemistry list and see which ones are the female ones, and I decided to choose one of them. And I didn't choose the oldest one because I figured it's not going to make any difference to somebody like Mildred Dresselhaus, whether she gets the Willard Gibbs or not. But it's going to make a big difference to somebody in mid-career. And so I did that, and I did a lot of research on the person, and I wrote up such a nomination package that which was different from everybody else's nomination package. Most other jurors would just submitted a CV. And so the first one was Jackie Barton. And she was amazed. She looked at the list of previous awardees, and she's so proud to be the one after Marie Curie. So I succeeded in doing three of them before I got off the jury. And one of them was Caroline Bertocci, who won the Nobel Prize last year.
Yeah.
Okay. So there are many good women out there. And I'm so glad that times have changed, that things have gotten better in terms of the proportion of women that are in the fields of science and engineering. Yes, I
Yeah.
used to go to a conference and end up as being one of two women in the entire 120 participants. Not anymore.
Yeah, yeah, that's good part. Still, we need to work on it to remove this discrepancy. I like to go to the next part, the beyond the lab part, and ask a few questions about the personal aspect of your life. So, what do you do at your spare time?
What do I do in my spare time? I do my garden. I have a garden in two lots, two adjacent lots, and they're all perennials. And I have flowers all the time. And I spend all growing season in my garden, except for 3 days that I go to university. I have been retired since 2006, January, but I still go to university 3 days a week because I like to work with students, PhD students, and help them out.
Yeah.
And try to keep my hand in so that I don't
Yeah.
lose all my brain cells. But I love my garden, and it's really something.
Yeah, that's very enjoyable, actually, the gardening and all these things. Yeah. So, what was your dream job when you were a kid?
Oh, I wanted to be a teacher.
Mm.
Yes, I wanted to teach math or science, physics. I actually like physics very much.
So you are living your dream now.
Oh, yes. I mean, I think I was extremely lucky in my whole career, my lifetime, to be able to well, first of all, I was hired to be a tenure track professor, assistant professor at a time when they were not hiring anybody or not even giving interviews to women. I I happened to apply to a brand new campus of the University of Illinois. They were just breaking ground. Basically, they had the building that I did my entire career in was not even built. There was nothing there, just an empty lot. Uh, when I was hired by a very forward-looking head, uh, and I don't know why he took a chance on me, but that made all the difference.
Okay, amazing. So, if there were another life, another parallel world, uh, and you could choose another job, what it would be? Which one you pick?
I'm not sure. I like what I did so much. I don't think I can pick something else. I don't think I could ever work in the private sector.
Mm.
I enjoyed very much being my own person, doing nobody telling me what to do, or having to please a direct supervisor, but plan my own work, and that you can only do as an academic. So
So,
I don't think I would have chosen anything else.
okay.
Yeah, but it
So,
has to be a combination of research and teaching. Teaching is not enough.
yeah.
So, is there anything that if you go back, you will change your decision? I mean, is there anything that you regret and you think that you could decide differently?
Not really. There are minor things. Like when I first started out, I didn't realize that female students needed special um, uh, handling because they were not as sure of themselves as the male students were. So I lost two brilliant female students that way. They gave up. And so that's one of my regrets.
Mm.
I could have done it better if I had only known. You see, I was so sure of how to do things because of the way I did it myself when I was a
Yeah.
graduate student, And so, my advisor, I only got to see him maybe 15 minutes every few months.
Mm.
So I was entirely on my own. But not all students can do that. And so that was one of my regrets, that I didn't realize my brilliant females would quit on me before they had a chance to show how good they are.
So if a time machine existed, would you go rather 200 years back or forward?
Not 200, that's too 100 years back. That's the golden age of physics, quantum mechanics,
Yeah.
Schrodinger, Born, the Broglie, those guys.
Yeah.
Those were wonderful times. I would have liked to be then in research.
Yeah.
The last question, who is your favorite scientist in the history?
Oh, I told you not to ask me that. Because I said it would be too trite to say Marie Curie.
No. It's okay.
No, she's such an icon. If I think of any one person that has served as a light beam to tell me how hard work you have to put in the hard work in order to accomplish things, and she did, even given the circumstances that she was in. Incredible.
Yeah, that's true. Well, thank you, Professor. Thank you so much for your time. And actually, I enjoyed this interview and found it educational, exciting. Is there anything that you want to add I didn't ask?
No, it's fine.
Thank you. Have a good day. Thank you.
You too.